Section 1 Introduction. We're here to discuss the recent advancements in the field of text-to-image models, which have significantly improved image editing and content creation. These models allow users to manipulate various aspects of both generated and real images. However, applying these advancements to video editing is still a work in progress. There has been a recent increase in large-scale text-to-video generative models, which have shown promising results in creating videos from textual descriptions alone. Despite these advancements, current video models are still in the early stages of development. They are limited in terms of resolution, video length, and the complexity of video dynamics they can handle. In this study, we aim to utilize a cutting-edge pre-trained text-to-image model to edit natural videos based on text prompts. Our goal is to create high-quality videos that follow the edits specified by the input text, while maintaining the spatial layout and motion of the original video. One of the main challenges in using an image diffusion model for video editing is ensuring that the edited content remains consistent across all video frames. In other words, each point in the 3D world should undergo coherent modifications over time. Existing video editing methods based on image diffusion models have shown that global appearance consistency across edited frames can be achieved by extending the self-attention module to include multiple frames. However, this approach doesn't fully achieve the desired level of temporal consistency, as the video's motion is only implicitly preserved through the attention module. As a result, professionals or semi-professionals often have to resort to complex video editing pipelines that require additional manual work. To address this issue, we propose a framework that explicitly enforces the original interframe video correspondences on the edit. Natural videos often contain redundant information across frames, such as similar appearances and shared visual elements. We've observed that the video's internal representation in the diffusion model exhibits similar properties. In other words, the redundancy and temporal consistency of the frames in the RGB space and in the diffusion feature space are closely related. Based on this observation, our approach aims to achieve consistent edits by ensuring that the features of the edited video are consistent across frames. We enforce that the edited features convey the same interframe correspondences and redundancy as the original video features. To do this, we use the original interframe feature correspondences, which are readily available from the model. This results in an effective method that directly propagates the edited diffusion features based on the original video dynamics. Our approach allows us to utilize the generative prior of a state-of-the-art image diffusion model without additional training or fine-tuning. It can also work in conjunction with an off-the-shelf diffusion-based image editing method. In summary, our key contributions are as follows. 1. We've developed a technique, which we call TokenFlow, that enforces semantic correspondences of diffusion features across frames. This significantly increases temporal consistency in videos generated by a text-to-image diffusion model. 2. We've conducted a novel empirical analysis studying the properties of diffusion features across a video. 3. We've achieved state-of-the-art editing results on diverse videos, depicting complex motions. Section Summary. In this paper, the authors propose a framework called TokenFlow that aims to improve the temporal consistency in videos generated by a text-to-image diffusion model. They achieve this by enforcing semantic correspondences of diffusion features across frames, ensuring that the edited video maintains the same interframe correspondences and redundancy as the original video. This approach allows for high-quality video editing without the need for additional training or fine-tuning. The authors also provide empirical analysis on the properties of diffusion features in videos and demonstrate state-of-the-art editing results on videos with complex motions. Section 2 Related Work. We're going to discuss some related work in the field of text-driven image and video synthesis. Pioneering efforts have used GAN architectures to create images based on text descriptions. As the amount of data and pre-training strategies in the vision language field have grown, we've seen significant improvements in the ability to generate images from text. This means users can now create high-quality visual content using simple text prompts. A lot of this progress is due to diffusion models, which are now considered the best tools for generating images from text. These models have also been adapted for generating videos from text by adding a time dimension to the 2D architectures, for example, by using temporal attention, and by training them on large video datasets. Recently, Gen 1 adapted a diffusion model architecture for video editing, by training the network on structure and appearance representations. However, these video diffusion models are still in their early stages and are mostly limited to short videos, or they produce lower quality visuals compared to image models, due to their high computational and memory demands. On the other hand, some recent promising work has used a pre-trained image diffusion model for video synthesis tasks without any additional training. Our work falls into this category, as we use a pre-trained text-to-image diffusion model for video editing, without any additional training or fine-tuning. When it comes to consistent video stylization, a common approach is to apply image editing techniques like style transfer to each frame, and then post-process to address any inconsistencies in the resulting video. While these methods effectively reduce flickering, they struggle with frames that have significant content variations, which often happen when using text-based image editing techniques. Caston and others have suggested breaking a video down into a set of 2D atlases, each representing the background or a foreground object throughout the video. Any edits made to the 2D atlases are automatically mapped back to the video, achieving temporal consistency with minimal effort. However, this method has limitations in its representation capabilities and requires long training, both of which limit its usefulness. Our work is also related to traditional work that showed that small patches in a natural video repeat extensively across frames. This means that consistent editing can be simplified by editing a subset of keyframes and spreading the edit across the video by establishing patch correspondences using handcrafted features in optical flow, or by training a patch-based GAN. However, such propagation methods struggle with videos that have changing lighting conditions, or complex dynamics, and can only function as post-processing. Our work shares a similar motivation with this approach, taking advantage of the temporal redundancies in natural videos. We demonstrate that these redundancies also exist in the feature space of a text-to-image diffusion model, and we use this property to achieve consistency. Section summary. Previous works have focused on text-driven image and video synthesis using GAN architectures and diffusion models. While video diffusion models are still in their early stages and have limitations in terms of computation and visual quality, recent works have shown promise by leveraging pre-trained image diffusion models for video synthesis tasks. Another related approach involves decomposing videos into 2D atlases to achieve temporal consistency in video stylization, but this method has limitations in representation capabilities and requires extensive training. Our work aims to leverage the temporal redundancies in natural videos and the feature space of a text-to-image diffusion model to achieve consistent video editing without the need for additional training or fine-tuning. Section. Controlled generation via diffusion features manipulation. We've recently seen a lot of research showing how text-to-image diffusion models can be adapted for various tasks, such as editing and generating images, by simply manipulating the intermediate feature representation of the diffusion network. Some studies have shown how to swap semantic appearances using diffusion feature correspondences. The study, Prompt to Prompt, found that by tweaking the cross-attention layers, we can control the relationship between the spatial layout of the image and each word in the text. Another study, Plug-and-Play Diffusion, PNP, analyzed spatial features and self-attention maps and found that they capture semantic information at a high level of detail. Tune A Video showed that by extending the self-attention module to work on more than one frame at a time, we can generate frames that have a consistent overall appearance. Some studies have used this property to make video edits that are consistent throughout the video. However, as we showed in Section X, simply expanding the self-attention module isn't enough to achieve detailed temporal consistency. Previous and concurrent studies have either had to compromise on visual quality or have shown limited temporal consistency. In our work, we also edit videos by performing simple operations in the feature space of a pre-trained text-to-image model. But instead of just expanding the self-attention module, we explicitly encourage the model's features to be consistent over time using a method we call TokenFlow. Diffusion probabilistic models, DPMs, are a type of generative model that tries to approximate a data distribution through a progressive denoising process. This process starts with a noisy image that follows a Gaussian distribution, and the diffusion model gradually denoises it until it becomes a clean image drawn from the target distribution. DPMs can learn a conditional distribution by incorporating additional guiding signals, such as text conditioning. Song et al. Developed DDIM, a deterministic sampling algorithm that starts with an initial noise. By applying this algorithm in reverse order, also known as DDIM inversion, starting from the clean image, we can obtain the intermediate noisy images used to generate it. Section summary. Recent works have shown that text-to-image diffusion models can be adapted for various editing and generation tasks by manipulating the intermediate feature representation of the diffusion network. While previous methods have focused on self-attention inflation, our approach explicitly encourages temporal consistency through TokenFlow, resulting in fine-grained video editing with improved visual quality and temporal coherence. Diffusion probabilistic models, DPM, approximate a data distribution through a denoising process, and can incorporate additional guiding signals like text conditioning for conditional generation. Section. Stable diffusion. We're going to talk about stable diffusion, SD, a well-known model used for converting text into images. This model works in a hidden image space. It uses a pre-trained encoder to convert RGB images into this hidden space, and then a decoder to convert these hidden images back into high-resolution images. The SD model is built on a U-Net architecture, which includes residual, self-attention, and cross-attention blocks. The residual block processes the output from the previous layer, while the cross-attention block adjusts features based on the text prompt. In the self-attention block, features are transformed into queries, keys, and values. The output of this block is determined by multiplying the attention matrix with the values. The attention operation calculates the affinities between the projections of the queries and values. Now, let's talk about our method. Suppose we have an input video and a text prompt describing the desired edit. Our goal is to create an edited video that follows the text prompt while maintaining the original motion and semantic layout of the input video. To do this, we use a pre-trained text-to-image diffusion model. If we simply apply this model to each frame of the video independently, we end up with inconsistencies across frames. However, we found that these inconsistencies can be reduced by ensuring consistency among the internal diffusion features across frames during the editing process. Natural videos usually show consistent content over time. We noticed that the internal representation of natural videos in our model has similar properties. For example, the features extracted from a given video show a consistent representation across frames. We also found that the original video features provide detailed correspondences between frames. We can even synthesize one frame by swapping its features with corresponding ones in a nearby frame. However, when an edit is applied to each frame individually, the consistency of the features breaks. Therefore, our main idea is to manipulate the features of the edited video to maintain the consistency and inter-frame correspondences of the original video features. Our framework, which we call TokenFlow, alternates between two main components at each generation step. I. Selecting a set of keyframes and editing them according to the text prompt, resulting in a shared global appearance across the keyframes, and E. Propagating the features from the keyframes to all of the frames based on the correspondences provided by the original video features. This approach has two main benefits. First, randomly selecting keyframes at each generation step increases the robustness to a particular selection. Second, since each generation step results in more consistent features, the selected keyframes in the next step will be edited more consistently. Section Summary. Stable Diffusion, SD, is a text-to-image diffusion model that uses a U-Net architecture with residual, self-attention, and cross-attention blocks. The model leverages a pre-trained encoder and decoder to map RGB images to a latent image space and decode them back to high-resolution images. To ensure consistency in video editing, the TokenFlow framework alternates between editing keyframes and propagating features from the keyframes to all frames, preserving the original motion and semantic layout of the video. Section. Pre-processing. Extracting diffusion features. We begin by processing the input video, which we'll refer to as I. We apply a technique called DDIM inversion to each frame of the video, which results in a sequence of latent features for each frame. These latent features are then fed into our model at each generation step, and we extract tokens from the self-attention module of every layer in our network. These tokens will later be used to establish connections between the diffusion features of different frames. Next, we move on to keyframe sampling and joint editing. Our research suggests that we can generate subsequent frames by propagating the features of a single edited frame to their corresponding locations. However, most videos cannot be represented by just one keyframe. To address this, we consider multiple keyframes and obtain a set of features, or tokens, from them. These tokens will later be propagated throughout the entire video. At each generation step, we randomly select a set of keyframes at fixed intervals. We then edit these keyframes together, extending the self-attention block to process them simultaneously. This encourages the keyframes to share a global appearance. In more detail, the input to the modified block includes the self-attention features from all keyframes. These features are represented as queries, keys, and values for each frame. The keys from all frames are combined, and an extended attention calculation is performed. The output of the block for each frame is then determined by applying this extended attention to the values of all frames. We define a base set of tokens, T_base, for each layer in the network. Each keyframe queries all other keyframes and gathers information from them. This results in a roughly unified appearance in the edited frames. Section Summary. In the pre-processing step, we extract diffusion features from each frame of the input video using DDIM inversion. These features are obtained by feeding the latent representation of each frame to the model and extracting tokens from the self-attention module. In the keyframe sampling and joint editing step, we consider multiple keyframes and propagate their features to the entire video to ensure a unified appearance. This is done by extending the self-attention block to process all keyframes simultaneously and aggregating information from them. Section 4.2 Edit propagation via TokenFlow. In Section 4.2, we discuss how we propagate edits through a video using a method we call TokenFlow. We start with a base set of tokens, denoted as T_base, and spread these across the video. This is done based on the token correspondences we've extracted from the original video. At each step in the generation process, we calculate the nearest neighbor, NN, of each original frame's tokens, represented as phi, x_t, I, and the tokens of its two neighboring keyframes, represented as phi, x_t, I plus, and phi, x_t, I. Here, I plus refers to the index of the nearest future keyframe, while I refers to the index of the nearest past keyframe. We then denote the resulting NN fields as gamma_I plus and gamma_I. These fields are calculated by finding the minimum cosine distance, denoted as d, between the spatial locations in the token feature map of the current frame and its adjacent keyframes. We apply this method at all time steps and self-attention layers, although we've left out the notations for the generation time step t for simplicity. Once we have gamma_PM, we use it to spread the edited frame's tokens, T_base, to the rest of the video. This is done by linearly combining the tokens in T_base that correspond to each spatial location P and frame I. The tokens are combined in such a way that they are proportional to the distance between frame I and its adjacent keyframes. This ensures a smooth transition. It's important to note that this process also modifies the tokens of the sampled keyframes. In other words, we adjust the self-attention blocks to output a linear combination of the tokens in T_base. To summarize our video editing algorithm, we first perform DDIM inversion on the input video, I, and extract the sequence of noisy latents for all frames. We then denoise the video, alternating between editing keyframes and propagating TokenFlow. At each generation step, we randomize the indices of a number of keyframes less than the total number of frames, n, and denoise them using an image editing technique combined with extended attention. We then denoise the entire video, J_t, by combining the image editing technique with TokenFlow at every self-attention block in every layer of the network. It's important to note that each layer includes a residual connection between the input and output of the self-attention block, so performing TokenFlow at each layer is necessary. Section Summary. In this section, the authors propose a method called edit propagation via TokenFlow for video editing. They use token correspondences extracted from the original video to propagate the edited frame's tokens to the rest of the video. This is done by computing the nearest neighbor of each original frame's tokens and its adjacent keyframe's tokens, and then linearly combining the tokens to ensure a smooth transition. The overall algorithm involves performing DDIM inversion, denoising the video using image editing techniques combined with TokenFlow propagation at every self-attention block in every layer of the network. Section 5 Results. 5 Results. We tested our approach on a variety of videos from Davis and the Internet, featuring animals, food, people, and different moving objects. The videos had a spatial resolution of either 384 by 672 pixels or 512 by 512 pixels, and they ranged from 40 to 200 frames in length. We applied different text prompts to each video to achieve a range of editing outcomes. Our test dataset included 61 pairs of text and video. We used PNP diffusion as the frame editing method, keeping the hyperparameters consistent across all our results. However, PNP diffusion sometimes struggles to maintain the structure of each frame due to inaccuracies in DDIM inversion. For instance, in one case, a dog's head appeared distorted, see figure, middle column, right frame. Our method helps to mitigate this issue, as it uses multiple frames to generate each frame in the video. Our framework can be integrated with any diffusion-based image editing technique that can accurately maintain the structure of the images. We have results using different image editing techniques available in the supplementary material, SM. For more details on implementation and video results, please refer to the SM. In the figures, you can see sample frames from the edited videos. Our edits are consistent over time and align with the editing prompt. For example, a man's head is transformed into a Van Gogh painting or marble, top left, while his identity and the background of the scene remain consistent throughout the video. Similarly, the patterns on a polygonal wolf, bottom left, are consistent over time, with the body always appearing orange and the chest blue. More video examples are available in the SM. We compared our method with several state-of-the-art and concurrent works. I. Text2 Video 0, which uses ControlNet for video editing through self-attention inflation. E. Tune Video, which fine-tunes the text-to-image model on the given test video. E. Gen 1. A video diffusion model trained on a large-scale image and video dataset. IV. Text-to-Live, which uses a layered video representation, NLA, and performs test-time training using clip losses. However, NLA requires foreground-background separation masks and takes approximately 10 hours to train. Therefore, we only compared with them on Davis videos where an NLA model was available. We also considered two additional baselines. I. Per frame diffusion-based image editing baseline, PNP diffusion. E. Applying PNP diffusion on a single keyframe and propagating the edit to the entire video. Section summary. The authors evaluated their method on various videos with different subjects and resolutions, using different text prompts for editing. They compared their approach to several state-of-the-art methods and found that their method improved the accuracy of preserving the structure of each frame in the video. The edited videos demonstrated temporal consistency and adherence to the edit prompt, with examples provided in the paper. Section 5.1 Qualitative Evaluation. We'll now discuss the qualitative and quantitative evaluations of our method, comparing it to 4 other well-known approaches. Please refer to the supplementary materials for the complete videos. In terms of qualitative evaluation, our method, shown in the bottom row of the figure, produces videos that closely follow the editing instructions while maintaining a consistent flow throughout the edited video. Other methods, however, struggle to achieve both these objectives. For instance, the Tune a Video method, second row, expands a 2D image model into a video model and fine-tunes it to match the video's motion. This works well for short videos, but for longer ones, it fails to capture the motion accurately, leading to nonsensical edits. When we apply the PNP method to each frame independently, third row, we get excellent edits that follow the editing instructions, but as expected, these edits lack temporal consistency. The Gen 1 method, fourth row, also suffers from temporal inconsistencies, such as the color change of the origami stork's beak. Moreover, the quality of their frames is significantly worse than that of a text-to-image diffusion model. The text-to-video 0 method, fifth row, results in severe jittering as it heavily relies on the extended attention mechanism to encourage consistency. We also compared our method to text-to-live and a method that propagates an edit from a single keyframe to the rest of the video. Text-to-live lacks a strong generative prior, resulting in limited visual quality. It also relies on a layered representation of the video, which takes about 10 hours to train and is limited to videos with simple motion. The method that propagates the edit produces artifacts on frames that are not near the edited keyframe. Moving on to the quantitative evaluation, we assessed our method based on 2 criteria: edit fidelity and temporal consistency. Edit fidelity was measured by calculating the average similarity between the clip embedding of each edited frame and the target text prompt. Temporal consistency was measured by calculating the optical flow of the original video, warping the edited frames according to it, and measuring the warping error. Our method outperformed the baselines in both these aspects. It achieved the highest clip score, indicating a good match between the edited video and the input guidance prompt. It also had the lowest warp error, indicating temporally consistent results. We also considered a reference baseline where the original video is passed through the LDM autoencoder without any editing. This baseline provides an upper limit on the temporal consistency achievable by the LDM autoencoder. As expected, the clip similarity of this baseline is poor as it does not involve any editing. However, this baseline does not achieve zero warp error either due to the imperfect reconstruction of the LDM autoencoder, which introduces high-frequency information. Section summary. The qualitative evaluation shows that our method outperforms 4 other baselines in terms of adhering to the edit prompt and maintaining temporal consistency in the edited videos. Other methods struggle to achieve both of these goals. In the quantitative evaluation, our method achieves the highest clip score, indicating a good fit between the edited video and the input guidance prompt, and also has the lowest warp error, indicating temporally consistent results. Section 5.3 Ablation Study. In this section, we're going to discuss an analysis we conducted on the main design choices in our framework. Firstly, we examined the use of a feature we call TokenFlow, which is used to maintain temporal consistency. In this test, we replaced TokenFlow with a feature called Extended Attention and applied it to all frames of the edited video. However, we found that this process was quite demanding in terms of computation and didn't work well with longer videos. Next, we looked at what would happen if we didn't randomize the selection of keyframes at each step of the generation process. Instead, we used the same keyframe indices, which were evenly spaced in time, throughout the generation. The results of these tests can be found in the table at the bottom of the page, and the videos we produced are available in the supplementary materials. What we found was that TokenFlow was crucial for maintaining a high level of temporal consistency. This suggests that simply extending self-attention to multiple frames isn't enough to achieve fine-grained temporal consistency. We also found that using fixed keyframes resulted in the video being artificially divided into short segments between the fixed keyframes. This had a negative impact on the temporal consistency of the result, as evidenced by the higher warp error. This effect can be seen in the videos we produced for this test, which are available in the supplementary materials. We've developed a new framework for editing videos based on text using an image diffusion model. We've explored how a video is represented in the diffusion feature space and shown that consistent video editing can be achieved by maintaining a consistent diffusion feature representation during the generation process. Our method outperforms existing methods, showing a significant improvement in temporal consistency. However, our method does have some limitations. It's designed to preserve the motion of the original video, so it can't handle edits that require structural changes. Also, our method relies on a diffusion-based image editing technique to preserve the structure of the original frames. If this technique fails to preserve the structure, our method enforces correspondences that don't make sense in the edited frames, leading to visual artifacts. Finally, the decoder we use introduces some high-frequency flickering. One possible solution to this would be to combine our framework with a better decoder. We've found that this minor level of flickering can be easily removed with existing post-processing deflickering techniques. Our work has provided new insights into how natural videos are represented in the space of diffusion models, and how these representations can be used to improve video synthesis. We hope that our work will inspire further research into using image models for video tasks and designing text-to-video models. Section Summary. In this section, the authors conduct an ablation study to evaluate the impact of two design choices in their framework. First, they compare the use of TokenFlow versus extended attention for enforcing temporal consistency in edited videos, finding that TokenFlow performs better. Second, they compare randomizing keyframe selection versus using fixed keyframes, finding that fixed keyframes negatively affect temporal consistency. Overall, their framework outperforms existing baselines in achieving consistent video editing, but it has limitations in handling structural changes and may introduce visual artifacts. Section 7. Acknowledgement. In the 7th section titled, Acknowledgement, we express our gratitude to Hila Sheffer for her diligent work in proofreading our paper. Section Summary. We express our gratitude to Hila Sheffer for her valuable contribution in proofreading the paper.